Today I'm going to talk about testing MQTT v5 or version 5 implementations. I've done a few talks this year about MQTT v5 itself and the differences between it and previous versions of MQTT. And that's a photo of me giving that talk in Singapore recently, in September. The whole video is on YouTube, so you can go and check that out if you want to do that. I intend to keep doing that on each of my talks and see how much of a regression I can get of photos of me doing previous talks. So I'm Ian Craggs. I work for IBM on the IBM Watson IoT platform, which uses MQTT to allow devices to connect to the platform and to send commands to them. I also work on Eclipse Parho, and I'm a project leader for that. I'm also on the Eclipse IoT PMC. I've been using MQTT since early 2000s, writing brokers and client libraries, and at the moment I'm responsible for the C client, the embedded C client, also for the MQTT SN C client and test material in Parho. The MQTT SN protocol is a variant of MQTT for non-TCP networks, and we're hoping to get that into the standardization process or start the standardization process for that next year. I'm also on the OASIS Standardization Technical Committee for MQTT, so I've had a lot to do with the standardization of MQTT version 5. So today I'm going to say a little bit about MQTT version 5, what are we trying to test, and my current approach to testing that for Parho and the client libraries that we have, and then some ideas for steps that could be taken for the future for testing. As I said, the full video is on YouTube, you can go and find it, as are all the other videos that were taken on the Eclipse IoT Day in Singapore. And there are 2 previous IoT days before Singapore this year, so all the videos are on YouTube for those as well. MQTT version 5. It's not that long ago since we finished the standardization process for version 3.1.1. So one of the obvious questions is, why do we need another version of MQTT quite so soon? And the answer is that for 3.1.1, we wanted to get the standardization process complete as quickly as possible, because MQTT had been around for 12 years, or maybe a bit longer than that, and people were concerned that it wasn't yet a standard. It was a specification, but they really wanted it to be standardized to be comfortable to use it. And so we got it through the standardization process as quickly as possible. That meant that we could make as few changes as possible to the existing specification. This meant that there were quite a few irritations or omissions from version 3.1.1 that people would like to see fixed and changed. And so version 5 is an attempt to fix all those outstanding issues that people had. And if we achieve that goal, that means we won't need another version of MQTT ever. That would be nice to achieve. I think that because they're different to a certain extent, that they will coexist for quite a while, but we've had quite a good take-up of version 5 already, even though it's just, haven't even finished the standardization process. So I think the outlook is good, that people will like it and pick it up. So we invented these large categories for the enhancements or the changes from version 3 to version 5. And so all of the items we grouped into these large categories that helped us think about all the changes that were going to be made. One of the biggest items is error reporting, because if anybody of you who have used version 3 knows, there are certain situations where any errors that are found are not available, can't be reported back to the other end of the MQTT session. In particular, with publish packets, there's no way of returning errors. So we fixed all of that. We've also allowed properties so that there's metadata available on all of the packets. And we've added some features to help out people implementing cloud-scale MQTT servers and for small clients, say on Arduinos. There are 14 packets in version 3 of MQTT. We've only added one more in version 5, which is for challenge response authorizations. I haven't actually implemented that in the C client yet, because I think that's something that people are going to be using later, but that's going to be coming soon. A little more detail about the version 5 enhancements into those packets. Yes, we've got properties in all the packets. We've simplified some of the operational session state. We've improved error reporting and helped out scalability and large-scale systems. So MQTT, from a testing point of view, is a client-server protocol. So we always have a server in the middle, which MQTT normally calls a broker, which is illustrated at the bottom of this screen. And we have clients that connect to it. In this case, we have a subscriber and a publisher. And this is from a little project of mine, a side project of mine, to visualize MQTT connections, which I'll show you a video of later on in the presentation. But I'm hoping to have that in an open source project soon. It actually works in 3D and in virtual reality, so on my Oculus Rift. So that's a little experiment that I'm playing with at the moment. So Paho supplies client libraries for MQTT. We don't have an MQTT broker apart from the test broker that I'm going to tell you about today, but we have client libraries in all of these languages. We've got a Ruby client just contributed, and I'm hoping we're going to have a formal release of that soon. And so our problem is testing all of these different languages, these client libraries, making sure that they conform to the MQTT specification and work well with all sorts of MQTT brokers. And so a test application is going to be using these client libraries and making sure that the responses from them conform to expectations. When we're testing these client libraries, then we have the opportunity to look at the interactions in two places. We have the library calls that are made from the application to the client library. And so this is normally what you would use if you're writing an application using one or more of these. So obviously we can write test programs which use these. We could also, while we're doing this, inspect the TCP packets that are being sent to and from the broker. And so if we're doing broker testing, we could use the TCP interfaces, the MQTT packets themselves, or we could use a client library and have that extra level of indirection and use all of those library calls. One of the approaches to testing a client library that's used by the Python library in Paho is to have a mock broker. So all that does is receive packets from the library and then make those packets available to the test program. The test program is responsible for checking that the details of those packets are correct and for sending the responses back. So all of the interactions are controlled by the test program. This has the advantage of the fact that you don't need an external broker. You just have this very simple mock broker. It has the disadvantage that all of that logic has to be added and explicitly written into the test program. Some people like that sort of thing. Personally, I'm not so keen because I think it limits the flexibility of the tests that you can write, and because you have to put all of those expectations into the test program, you're sort of second-guessing yourself all the time. So what I prefer to have in my tests is to have a real MQTT broker, and then we have a test which just deals with the library calls, and the only interaction it has with the test broker is some test setup, so maybe it has some configuration for the broker. But of course, you need a test broker to be able to do that, or you need a broker to test with. And when we had version 5, the new specification, there were no MQTT brokers that had implemented that specification. So what was I going to do? As it happens, I'd already had a Python broker that I'd written for version 3.1.1, so I extended that. It's available in this GitHub repo, parho.mqtt.testing. It's written in Python, so all you need to do to run it is to clone that repo, and then it's start the Python program. This is a snippet of the code of the implementation of that broker. It's, as I said, written in Python. I tried to write it in such a way that it was as clear as possible how the broker operation would work. So the goal was to make the code clear, not to make it clever or high-performing. As a test broker, this goal, we weren't trying to make it scalable. We were just trying to make it conform and implement the MQTT protocol as closely as possible. And one of the ways that I thought about making it correct as possible was not only by running tests against it, but by making it the code clear so that people could come along, look at the code and inspect it, and maybe if they were implementing a broker of their own, look at it as examples of how this could be done. And then by looking at the code, people could also find problems. You'll notice that we've got some statements embedded into this code, which are actually MQTT conformance statements, and I'm going to come along and mention those a bit in more detail in a bit later. So why did I choose Python for writing this broker? Well, I've been using Python for, again, since about the year 2000. And the reason that I started using Python was that I'd been using Rex, a programming language written by or developed by IBM, for a long time, up until at that point. And then Perl became popular in the group that I was working in, and I was never comfortable using Perl. So I decided to look around for an alternative. And at the time, I found some comparisons of the features of different programming languages, and Python came out near the top of every one. It wasn't at the top of any of them, but it was near the top. So I decided to have a look, and I've been using it ever since. And when I'm using Python, I think of it, it's quite like the pseudocode that we were often using in classes when I was a fledgling programmer in the 1980s. So it was comfortable for me to use, and I think of it as being almost like pseudocode, so that it's easy to read. It also has supports for multiple programming paradigms, functional, object-oriented, those sorts of things. So you can write concise but readable code. It also has a large standard library, so implementing certain features in Python is orders of magnitude faster than some other languages. Well, certainly than C. I use C a lot. Implementing TLS as a server in Python took me an hour. In C, it took me weeks to add OpenSSL support into my C library. That was a nightmare. So it's easy to implement lots of features, so it's great. Obviously, Python itself is open source, and I saw a report recently where it's getting even more popular than it was before. I thought it was going to be overtaken by Ruby a few years back, but that seems to have not happened. So this is how you start the broker. There's a script to start it, and then there's a configuration file. This is what you would see if you use this localhost testing configuration file. You see that it's got an MQTT 3.1.1. Implementation, also an MQTT v5 implementation, and also the start of an MQTT-SN broker. I wrote a combined version 3 and MQTT-SN broker a long time ago, so I've been disappointed that there hasn't been one that's been produced since then. So It's one of my other side projects to complete the implementation of MQTT so that we've got a combined one at this point. So maybe this Python broker won't be just a test broker, but it'll be something that can be used for real work as well. Also, you'll see at the bottom, we've got a variety of listeners with different TLS configurations for testing. And this broker supports WebSocket as well. And we are using it currently for the CI testing in the PAHO C client and the PAHO Java client. And because it's written in Python, it runs anywhere that Python does. So this is the Travis configuration file for the C client. You can see that I clone the repo, and then I just start the broker, then it's available for testing. So one of the features of the broker is it's if you turn debug on, then you can see all of the packets that are being sent and received. So this is the PAHO C client command line utility, which has the same command options as the Mosquito command line utility, but I've recently added MQTT version 5 support, which is what this v-v5 means at the top. So we've got a very simple scenario of connecting, subscribing, and disconnecting. And on the broker output, when we turn debug on, we can see all the details of the packets, including, if we had any, the new MQTT v5 properties, the reason codes that are sent back, and all the other details of the packets. There's also an option to have message sequence charts output, so any of the sequences of exchanges of packets, you can output them as message sequence charts using this tool from this website. I think I should be able to go back to this. So one of the other features apart from that, here we go. Message sequence charts. This is from that visualization tool I was talking about. This is taken from a live feed from the broker. So this visualizes packets being sent between the clients and the servers. In virtual reality, if you've got an Oculus Rift, and I've had plans for improving this, being able to go inside the broker, look at the details of messages and the like. So that happened quite quickly. So I think what I did there was to slow it down so that you can see more of the details of the packets being sent and received. So that those are pings. And now we should send a publish. And this QoS2, so you see the acknowledgement packets being sent and received as well. So again, that was taken directly from a feed from the test broker. So there are a variety of options for visualizing the scenarios that you're using in the middle of your tests. So other things I put into the broker, it's got configurable behaviors. Some of these, the first of which are in version 5, new features to allow the maximum QoS that the broker supports to be specified, and then on the connect exchange, you can tell the client application the maximum of these limits that they're allowed to use, whether it's the packet size, the max number of outstanding in-flight messages. In version 3, you could do this, but it wasn't explicit. So in version 5, everybody knows what's going on, and both the server and client can tailor the behavior on the basis of the information that they're given. Some features that are added to the test broker that you wouldn't normally put into a production broker, deliberate errors, for instance. So we want to be able to test what happens if you send back a packet that's malformed and make sure the client libraries can handle those sorts of things. All of these configuration options are handled by a configuration file at the moment, but I also have an HTTP implementation or the start of it, so that you can change these things or this configuration while it's running. What I showed you before was not the complete broker output, because it also has these conformance statements, these statements starting with MQTT or MQTT v5. So as you run a test or a sequence of commands input, then these are output as well. And what these are are taken from the specification. There's a section in both the 3.1.1 and version 5 specifications for MQTT, which has conformance clauses in. These are all the must and should statements extracted from the specification into a nice appendix, so you can see a whole list. And the list looks like this sort of thing, but there's about 120 of these statements in version 5 specification. So you can see the first one or second one on this list is a UTF-8 encoded string must not include a null character. So what I've done is embed, I haven't finished this process of version 5. I've got about a third of the way through. It takes a while to add them all in. But I've embedded all of these conformance statements into the code for the broker. So when you run a test or a sequence against the broker, it tracks whether you've met that or encountered that conformance statement, and then gives you a report at the end of how many of these you've met. And some of these might have a good path and an error path, so there might be two cases for some of these conformance statements. So at the end of the broker run, it tells you how many you've achieved, how many you've met. And this was from a run of that very simple short sequence of that subscribe program, so it didn't cover very much. But as you can see, even with that short sequence, it's quite easy to get up to mid-50s or 60s, perhaps, percentage of coverage statements. It's far harder to get exceptions because you have to work at reproducing all of the error possibilities. So these conformance statements can be used as a test suite coverage measure and to improve your existing or newly written test suites. As I said, it's easy to achieve the mid-50s or 60s percentage-wise coverage, and it gets increasingly harder as you get nearer to 100%. If anybody of you in the room has ever tried to increase code coverage in a test suite, you'll know how hard it is to get that final 10% or 5% of coverage. And error coverage is hardest to measure because you tend to have to write specific tests for that particular error. Otherwise, you won't accidentally meet it. This is the output from that broker of the current PAHO C-client test suite. So I hadn't run this analysis until I got to the end of the test suite. And as you can see, I've got about 75% coverage. I haven't finished the MQTT v5 instrumentation yet, so these figures aren't quite complete. But as you can see also, I've got a pretty low coverage of the exceptions, so I have to work harder on that. I just did this out of interest. I also did the actual code coverage for that same run, and it turns out we've got about 72% code coverage, but you can see that's pretty similar to the coverage statements. So we've got mid-70s for the coverage statements here, but it's a lot different to the number of exceptions. So code coverage is one of the things that code coverage wouldn't necessarily tell you, is for specific scenarios, including exceptions and errors. That's the conformance statements can help you focus in on the improvements that are really needed in the test suite. So this gets to where that's where we've got to so far. I'm using that coverage approach in the PAHO test suite so far, and that broker is used in our CI tests. And you can go and use it if you want to implement an MQTT version 5 client. You can use that broker to test against. What I have done in the past is use this to generate test suites for brokers. So with the addition of a test input model, which limits the number of options of all the input values that you can take. For instance, if you're choosing which lengths of messages that you want to publish, the maximum length of message in MQTT is 256 megabytes. So you could imagine having a random test which tries to execute all of those, but that's a pretty big input space. So you want to narrow it down a bit. So that's what the test input model does, it narrows it down. And then with the input model and the MQTT broker, which will tell you the results, the expected results for any input, you can combine those together into a generated test, which looks something like this. This tells you the coverage statements that were achieved during that test. And then we have call statements, which are the test inputs, the results from them, and then some observations. So we have a call here, which is an MQTT connect with the parameters along with it. And then the observed event is the CONAC from the broker that was resulted, that came out of it, again with its values that need to be checked. And we get down to here, and this test ends because we send the second connect on the same socket, and that causes an error in the broker, and that's the complete test. So this can be run against any broker as a conformance test, and we can build up a whole test suite like that. That's comparatively easy for brokers. For client libraries, it's a bit harder because each of the client libraries has a different set of interfaces, has a different API. So I have an idea how to do this, but I haven't implemented it yet. But the generated test needs to be in some sort of abstract form, maybe in a language like Cucumber, which is a business, well, it's promoted as a business-oriented test language. And then if we do that, we would need abstract to concrete converters for each of the client libraries. Or maybe I could use that description of a test that I just showed you. Maybe I could use that as the abstract test. I haven't decided yet. Some of the pros and cons of generated test suites. I think the pros are that you tend to get a more complete and accurate test suite. People get bored. I mean, I get bored writing a test suite by hand. It's very difficult to get to the end of that. I think they can potentially be more flexible and have more combinatorial features. Potential cons, and people tend to, these reasons that are raised whenever I've talked to people about this in the past, is that the reasons for a specific test can be hard to explain, although I think the conformance statements can explain some of that, help to explain that. Also, if you have a long input sequence, then debugging the fundamental cause of of finding an issue can be hard. So if you have an input sequence and it takes 2,000 steps to find a problem, then really we would like that to be shorter. And one way we can do that, which I've used in the past, is an approach called delta debugging, which is very simple when you think about it. It's one of those when I read it, I thought, oh yes, why didn't I think of that? But I didn't. So if we imagine if we start off with a test instrument sequence of, say, 2,000 steps, and we basically do a binary chop at each stage. So we take it in half, then we leave out the first part, just execute the second, and also execute the first. And if we manage to reproduce the same problem, having omitted some of the sequence, then we know that part of the sequence, that subsequence, wasn't important. So in this step, if we execute this part of the test sequence, and then that part, omitting this, and we still manage to reproduce the problem, we know that this wasn't important and we can drop it. And we keep doing that for smaller and smaller subsequences until we get the smallest possible subsequence or sequence that can reproduce the problem. I've used this in the past to reduce sequences from 1,000 steps to about 15. And once you've got that smallest sequence, then it's usually very easy to understand what the root cause of the problem is. So that search that I used to generate the test suites in the past, I've wrote my own algorithms, and then since then I've realized that really they're a variant on Monte Carlo tree search. So I'm going to use that as a more formal way of implementing them in the future. And finally, when I was testing as a full-time job, my goal was to have it entirely automated, and so that I would just be sitting there pressing a button, and I would be automated out of a job. So it would look pretty much like this. You'd have a delta debugger sitting in the middle, so it shortened the test sequences. So when you found a problem, It might be a long sequence. You've shortened that to the smallest amount of steps that were required to reproduce that problem. You would add that to the bug recognition characteristics in the bug database, so that when you got a fix that came along, you could just say, oh, I'll just rerun this shorted sequence, see if it's really fixed or not. And then when you had some new features delivered, you would also have it described in the test oracle, or the broker in this case for MQTT, and the test input model added, and then slot that into your execution system, and away it would go and be able to formulate and do all the work for you. Obviously, adding a test input model and test oracle is still a significant, well, it's an interesting piece of work for a human tester, I think. So that's the end of my talk today. Thanks very much.